Hello, everybody. My name is Dr. Curtis Freeland Jones, and this is Principles of Chemistry 1, also known as Chemistry 103 at SUNY Adirondack for the summer 2020 session. We will be doing the entirety of the course in an asynchronous online style, meaning that I will upload video lectures for each of the units once a week. In addition, I will be uploading a video demonstration of the laboratory for that week and an online quiz covering the material that we cover in lecture and lab. Additionally, I will be posting online exams every 4 chapters and a final exam which will be modeled after the ACS standardized general chemistry exam, and that will be administered at the end of the summer session. Now, this course I mentioned includes both a lecture and a laboratory component. Now, the fact that we've been forced to go online due to the pandemic and quarantine means that the laboratory will be executed in a slightly different manner than you may be used to. I will be providing digital copies of all of the lab reports and chapters from the lab manual, although I think you have been instructed to purchase hard copies of the lab manual as well. We will do the experiment together with me leading you via video, and then you will take the data that I provide for you and complete the analysis section and the questions in the lab report and return that to me within a week. And that will be how we do labs this semester. The first 2 labs are fairly simple, but they become more difficult as the semester goes on, and you will be expected to understand how all of the labs work, and you will be tested on them. This is the way that we make sure that you actually participate, and instead of just ignoring that part. So we will be covering topics such as atomic structure, chemical bonds, reactions and equations, properties of gases and liquids, changes in state, heat changes, solutions, pH, and stoichiometry. The laboratory will be focused mostly on development of measurement techniques, also the collection of data and the development of theory via observation. This is obviously an introductory course, so the goal is to give you a broad exposure to many different parts of chemistry without focusing too much detail on any one specific part. At the end of the day, this is hopefully interesting and fun for you, but I understand that many people take chemistry only because they're required to, so I won't hold that against you. There won't be missed exams and quizzes because all of them will be online. You'll have a week to complete them. I hope that that's enough time. Also, they're completely open book because the style of this course is not meant to be punitive, but rather instructional. So I hope that you will consult sources and learn the material that's presented to you in the quiz questions. There's no attendance policy this semester because obviously you're all going to be diligently following along at home because you're not allowed to go anywhere. And we won't be using cell phones in the lab because we won't be in the lab. If you have any disabilities that you need accounted for, please contact me via email and I will make the appropriate accommodations. Although I believe that this video will be closed captioned and publicly accessible for anybody who needs to access it. So there will be 3 exams. There'll be 300 points total, meaning each of them is 100 points. There will be 300 points worth of quizzes, most likely 20 points each, and there will be 200 points worth of labs. There are 12 experiments, but I will take the best 10 of those 12 and apply that to your lab grade. Additional points earned will be directly applied to your total, and that will hopefully bump your grade up if you decide to do those extra lab reports. And then the final will be worth 200 points, bringing the total to 1,000, which is a fancy way of representing 100 points with decimals. Numerical grades are standard. Above a 92 is an A, and then onward down below a 60 is an F. So that's a failing grade. Everything else is passing. And academic honesty is expected in all activities, so don't have your friend take the test for you. That's considered a bad move. Now, this schedule here is a loose and hopeful schedule for the semester. My plan is to upload 1 chapter a week worth of lectures and allow you to consume them at your leisure. And I have a feeling that they were going to stick pretty closely to that. So, course objectives. You should, at the end of this course, understand the scientific process, including observation, hypothesis development, measurement, and data collection, experimentation, evaluation of evidence, interpretation, and mathematical analysis. You should be able to apply scientific data, concepts, and models in chemistry, recall key facts and basic theories in the field of introductory chemistry, demonstrate an ability to work collaboratively on science projects. You won't be doing that because you won't be working collaboratively because we must maintain proper social distancing. You will be expressing in writing an understanding of basic chemistry concepts, including the classification of matter, the mole, which is a quantity, chemical and physical changes related to energy related energy concepts, behavior of solids, liquids, gases, and solutions, chemical structure and function. You should be able to perform dimensional analysis, calculate density, also make stoichiometric calculations, and also pH and titration calculations. You will demonstrate your ability to work safely and effectively in the chemistry laboratory by completing your lab reports properly and answering questions on exams. And you will be applying laboratory skills by doing take-home projects that I assign sometimes for some of the easier experiments and sending me photos of yourself doing them. And you'll build and interpret simple models of molecules. You will apply course-specific knowledge to address emerging social and scientific concerns in the fields of advanced manufacturing and information technology, as well as other things such as environmental science and medicine. And you will analyze data derived from chemical experimentation, and you will abstract and interpret chemical information from curricular materials. In the laboratory, we will follow roughly the schedule shown below. I mentioned before the 10 of 12 labs being graded and the rest being extra credit. The lab manual has all of these experiments in it. However, they're not necessarily labs 1, 2, 3, and 4. I will post PDFs of all of these as we get to them. And this Thursday will be a density and specific gravity lab. It's a very simple lab, but it's meant to get everybody on the same page with regards to laboratory techniques and what various devices are called and how to take measurements. Oh, and I forgot to mention above, the textbook for this class has been listed previously as the Timberlake textbook, which some of you may have purchased. That is perfectly acceptable for you to use. You are not required to purchase it, so if you are short on cash right now, we have something called the Open Education Resource Textbook, which is an open source PDF and also online interactive textbook put out by some very nice nonprofit organizations. It's shown here. It has been compiled by SUNY Adirondacks Charlie D'Souza, who is a faculty in the chemistry department. This is a very nice, useful textbook full of good information and also full of not costing $200 or $300. I have no idea what Timberlake costs because I've never purchased it myself. And I would never expect anybody to spend that much money on a book when basically the same book is available right here. They start out with a spiel about this whole project called LibreTexts, which is a free textbook resource for many subjects, not just chemistry or even not even just science, but all branches of learning. And then there's a table of contents which lists the chapters in order along with the topics covered in each one of them. Now, one thing that would be nice about this PDF is if you clicked on those links and they brought you to the page in the PDF where the chapter is located, but what it does instead is it loads the web page and brings you to the chapter online, which is still sort of useful, but it's not as useful as a linkable PDF. However, it's only 300 pages, so it shouldn't be too easy to scroll to where you need to go and get the information that you need. I will also be posting all of the PowerPoints on the Blackboard webpage as we go along, so you'll be able to follow along with my lectures. So that's the textbook. That's the syllabus. And today I'm going to cover Chapter 1 in its entirety. It's a basic introduction to chemistry and the ideas of measurement, the various units that we use, and the types of math that you'll be expected to perform in the course of completing Chemistry 103. So beginning, what is chemistry? Chemistry is the study of matter, and matter is the substance of the universe, the material world, the basic building blocks of the universe. Now, matter can be described in a number of ways. The first is by describing its composition. The composition of matter is the specific substance that it is composed of. So whether it is sulfur or phosphorus or water, those are all different types of matter. There is also the structure of matter, how the particles of the substance are arranged in space and how they move against one another, if it's something like a gas or a liquid. There are also intrinsic properties that substance has that makes it what it is. Things such as the number of protons in the nucleus determines which element in the periodic table a substance is. Something like the number of electrons in a molecule determines things like its reactivity. Which brings us to the fourth description of matter that is covered by chemistry, which is the reactions of substances with each other, or even how singular substances change over time into other substances. There are a number of branches of chemistry. Physical chemistry just studies the physical properties of chemical reactions and substances, determining things like the hardness of an iron colloid or the amount of heat released by a combustion reaction. Analytical chemistry is concerned with determining the amount of trace elements dissolved in water, for instance, or determining specifically what elements a material is composed of. Say if you find an unknown material in nature that you want to identify, you would consult an analytical chemist. Inorganic chemistry is the study of non-carbon containing molecules, things such as salts or oftentimes metals, and various reactions of those chemicals. Organic chemistry studies carbon-containing molecules, which may form the backbone of much of the natural world. And biochemistry studies the chemistry of living processes, which are often composed of many principles of organic chemistry as well as the other branches of chemistry. And here you see a picture of a guy pipetting a sample into a cuvette. So chemistry happens in nature around you all of the time. We can either have chemical reactions that happen spontaneously or happen as a result of a natural process, or we can cause them to happen ourselves, such as when we cook or bake food. When you add chlorine to a pool, a chemical reaction happens. Batteries run on chemical reactions to produce electricity. Salt, the process of salt keeping the ice off of sidewalks is a chemical reaction between salt and water. And bleach removes stains from clothing via chemical reactions. In nature, things like fermentation by microbes is an example of a chemical process. Many microbes will convert sugars into alcohol, for instance, or into lactic acid. Photosynthesis is another chemical process where plants convert sunlight and carbon dioxide into sugar. And then leaves changing color because of pigments in between the chlorophyll molecules. That's also an example of a chemical process, of a natural chemical process. Now, there are non-natural chemical processes which happen in laboratories and in manufacturing, such as gasoline refining or distillation. Also, development of synthetic fibers is a laboratory chemical process. The development of pharmaceuticals is often completed in industrial facilities. Some pharmaceuticals are derived from natural products, but many of them are heavily modified to make them more biologically active. Water purification or water softening is another chemical process that is done in large industrial facilities. And agriculture is now often done industrially at a very large scale using pesticides, fungicides, and herbicides, all of which are chemicals. Additionally, fertilizer is a chemical, as well as all of the processes within the plant itself. So, everything around you is composed of chemicals. So, a chemical is a material used or produced in a chemical process, whether by laboratory, manufacturing, or natural processes. And a substance is a chemical that consists of one type of matter. We sometimes call this a pure substance. If it consists of two or more bound elements, then it is a molecule. But regardless of the fact that it contains bound elements, it's still one substance, and it has the same composition and properties throughout. Substances that were developed by chemists are in use every day, things like soap, toothpaste, lotion, clothing. And this is a fun little Venn diagram which shows the same two molecules that made by both natural and synthetic methods. So you have vitamin C, which is naturally occurring in oranges. It's also known as ascorbic acid. And alcohol, which occurs in naturally fermenting fruit. Now you can have the synthetic version of that, where vitamin C is made from glucose in a lab, or you can have a fully synthetic pathway for alcohol where it's made from ethene and steam. And then there's a crossover for alcohol because when you create a human-controlled fermentation using yeast or bacteria, you're harnessing a biological process which is technically natural, but you are stimulating it beyond what it may naturally be capable of producing. And so it's sort of both natural and synthetic. And here's a picture of all the chemicals in your kitchen. So you have fruits. They are grown with fertilizers and pesticides. They contain sugars and other carbohydrates. You have natural gas. You have natural polymers. You have metal alloys. You have chemically treated tap water. And you have silicon dioxide or glass, as well as the granite countertop, which is a complicated chemical structure, which we won't get into right now. This brings us to science in general. The idea of using experiment to explain our surroundings and our internal world. The organization of facts and their explanation in a systematic and logical manner is characteristic of science and the scientific method. And it is our attempt to understand the world without resorting to superstition, but rather observation of physical evidence and the creation of experiments to simulate events under controlled conditions. Science is done by making observations of nature, possibly taking rudimentary measurements, developing a hypothesis to explain those observations, and then designing experiments with procedures that test the hypothesis. Once the experiment is completed, one might develop a theory which generally consists of a model that describes how the observations occur based on the results of the experiment that you completed. Here is a flowchart showing that process. So you always start by seeing nature and making an observation. Then you develop a hypothesis. You may then undergo multiple experiments, refining your hypothesis each time in order to zero in on the correct explanation for your observations, which then results in, if you're good, a theory. Now, there's a lot of discussion about hypotheses versus theory, and also the idea of a scientific law. So a hypothesis is an educated guess. It is not based on, it's based only on observation. It's not based on any sort of systematic experiment or examination. Hypotheses can be disproven, but they can never be proven, and they can be supported with experimental evidence. Theories are summaries of hypotheses that are supported by experiment. They provide a good explanation of the phenomenon, but they can be disproven with conflicting evidence, which is how good science is done. You start with a theory and you refine it over time. You add or subtract corrections until you have something that explains all of the available data, at which point it becomes a scientific law, which is often involving a mathematical proof of some kind. Now, just because you can mathematically prove something doesn't mean that it is 100% true. It just has no counterexamples that are known. Many people spend their lives looking for counterexamples of many physical laws to varying degrees of success. A famous example of that is Einstein, who first discovered that time was relative and then spent the rest of his life trying to disprove it, but did not succeed. So the heart of the scientific method is experiment, which entails measurement and collection of data. There are two types of experiments. There are qualitative experiments where you merely obtain a description of a system that doesn't have any rigorous mathematical validity to it. And then there are quantitative experiments where you measure precisely and you obtain fixed relationships between parameters that you have controlled within the experiment. Measurement obviously involves a measuring device, which differs for the type of measurement that you're doing. You can use a meter stick to measure length, a scale to measure weight or mass, a thermometer to measure temperature. And such a device is calibrated to compare the object to some standard. And usually this is done in the factory, but some higher sensitivity devices need to be recalibrated from time to time by a certified professional or the owner of the device, depending on their skill level. Quantitative observations have two components, a number or magnitude and a unit, which is the dimensions of the measurement. Units are a standard and accepted quantity that is used to describe the type of measurement being done, and it describes the things being counted. If you don't use units, then measurements become very confusing. For instance, you wouldn't tell someone you need 6 of sugar because they wouldn't know whether you meant teaspoons or ounces or cups or pounds. So, in science, we take measurements with a number accompanied with a unit, which 4 nice examples are shown here. Meters, 35 meters, 0.25 liters, 225 pounds, and 3.4 hours. So, oftentimes you'll encounter metric and U.S. imperial units. We'll be using the metric system and the System International, or SI, unit system in this class, which is a decimal system based on factors of 10. It's used throughout most of the world and used by all scientists. It's easier to standardize because everything is factors of 10. So 1 liter is equal to 1,000 milliliters of water, which has a density of 1 gram per milliliter. So it's also equal to 1,000 grams. Water boils at 100 degrees Celsius. It's all very neat. And therefore, it's easier to convert between units because of this. So, in the metric and SI systems, 1 base unit is used for each type of measurement. And then you modify that with a power of 10 prefix or suffix to make larger or smaller units. So, the various measurements, length, volume, mass, time, and temperature, are covered in metric by the meter, the liter, the gram, the second, and the degree Celsius, respectively. And in SI, the only differences are, well, there's 3 differences. The cubic meter is used to represent volume, the kilogram is used to represent mass instead of grams, and the Kelvin is used to represent temperature instead of degrees Celsius. The difference between Kelvin and degrees Celsius is that Kelvin starts at absolute 0, and degrees Celsius starts at the freezing point of water, which is 273.15 Kelvin. This is a table showing examples of powers of 10, both greater than and less than 1. So 1 is 10 to the 0 power. 10 is 10 to the first power, and so on. 1/10 is 10 to the minus 1 power. And 0.01 is 10 to the minus 2 power. So this is going to be important when we start talking about scientific notation representing small quantities. These negative powers of 10 represent fractions of 1. And then there are prefixes that go with these factors. Some examples here that we use often in science, things like centi, which is 1/100th, milli, which is 1/1000th, micro, which is 1/1,000,000th, and nano, which is 1/1000,000th. Other ones are kilo, which is 1,000, and mega, which is 1,000,000 of something. So the first measurement that we do is length. And we use meter to measure length in science, which is slightly longer than a yard. It's 39.4 inches. And nowadays the meter is defined according to the speed of light, which we won't go into in more depth right now, but it's a fun thing to know. And a centimeter is 1 inch is equal to 2.54 centimeters. Volume is measured in liters or milliliters. The volume is the three-dimensional space occupied by a substance. We don't typically use cubic meters in chemistry because a cubic meter is a very large volume. We'll often use liters instead. Sometimes we'll use milliliters. And we measure volume using a graduated cylinder. Some basic conversions here. 1 liter is a little bit more than a quart, or 1 quart is a little bit less than a liter. And 1 milliliter is equal to 1 cubic centimeter. Mass is measured on a balance or a scale, and it is a measure of the quantity of material that a sample contains. A kilogram is 1,000 grams, or 2.2 pounds, and 1 pound is equal to 454 grams. Sometimes in the SI system, the kilogram will be used for larger masses, but we will be using grams for the most part in this class because it's easier to represent the size of chemical samples that you normally encounter. Temperature is measured in kelvins or degrees Celsius. We will usually deal with differences in temperatures in this class, but when measuring an absolute temperature, we'll use Kelvin. The reason that 0 degrees is set where it is that's the freezing point of water. Fahrenheit scale is based on a different substance, and therefore the numbers are different for water. And like I mentioned before, the Kelvin scale starts at approximately minus 273 degrees Celsius. Time is measured in seconds, and a fun fact about the second, it's now based on something called the hyperfine transition of cesium-133 atoms, also known as the atomic clock. That is probably gibberish to most of you if you don't have any basis in science, but we'll talk about what that means when we talk about nuclear chemistry. Time is generally measured using a stopwatch, hopefully more accurate than the one being shown here, but this one actually might be more accurate than some digital stopwatches if it's well made. Scientific notation is another thing that's important for representing quantities in science and chemistry. It is a number, also known as a coefficient, followed by a power of 10, shown as times 10 to the n power. This is a number in scientific notation, 7.03 times 10 to the second power. The coefficient is 7.03. The exponent is 2, and the exponential term is times 10 to the 2. If a number has a negative exponent, then it is less than 1. And if it has a positive exponent, it's greater than 1. Scientific notation is useful for representing very large or very small quantities. For instance, the number of water molecules in a cup of water is astronomically large, and each of those molecules has an astronomically small mass. So those numbers there that have many zeros in them can be represented in scientific notation much more compactly as 7.91 times 10 to the 24 molecules and 2.99 times 10 to the minus 23 grams, respectively. Writing in scientific notation. So if you have a number that you want to convert into scientific notation, find the decimal point and then move the decimal point to the right to make your number between 1 and 10, and then add the term times 10 to the minus n, where n is the number of places you moved the decimal point. It has a negative sign because the number is less than 1. For large numbers, you do the opposite. You find the decimal point and move it to the left to make a coefficient between 1 and 10, and then add the times 10 to the n term, where n is the number of places you moved the decimal point. Likewise, converting back to a standard number from scientific notation involves finding the sign of the exponent, n, determining whether it is positive or negative, and then moving the decimal point in the appropriate direction, either right for positive or left for negative, until you have made a number with either a large number of leading zeros or a large number of trailing zeros. If you want to put scientific notation into a calculator, you can do so. Oftentimes there is an EXP or EE key. So if you want to put in 4 times 10 to the 6th power, for instance, you would type 4 E or exp 6, and the calculator would show most likely one of these 3 displays to indicate the number that you just entered. Likewise, if you wanted to do 2.5 times 10 to the minus 4, you would type 2.5 EE plus minus to add a negative sign and then the number 4, and it would be shown like so. And then here is another example. So when you measure numbers, there will be significant figures involved. And when you measure numbers, there are 2 types of numbers that you measure. There are counted numbers, which are exact, and there are measured numbers, which have some error associated with them. So exact numbers are known with certainty. They have an unlimited number of significant figures and do not decrease the precision of a measurement. They are either counting numbers, things like 10 beds, 6 pills, or 4 chairs, or defined numbers like 100 centimeters equals 1 meter, or 12 inches equals a foot, or so on and so forth. Measured numbers always have uncertainty because they involve the reading of a measuring device, and your eyes have to guess what the number actually is. There's also uncertainty built into the tool because nothing is perfect. Some tools are more precise than others because they have smaller markings, such as these 2 rulers. You have to guess the value between these 2 smallest divisions on a measuring device. So each person will estimate it slightly differently, and this introduces a distribution of results. You can see ruler A is less precise than ruler B because ruler B has tenths of a millimeter in it. Although I dare you to find a ruler with tenths of a millimeter shown, but it's an example. So here you see this, you can measure between 2.8 and 2.9 centimeters. But this one you can measure 2.85 centimeters because this ruler is more precise. So indicating the uncertainty of a single measurement, scientists use a system called significant figures. This is all of the digits known with certainty plus one digit that is uncertain. The last digit is the number that is considered to be uncertain and is, unless stated otherwise, plus or minus 1. So non-zero integers are always significant. So things like 1 or 150. Zeros may or may not be significant depending on where they fall. If they are leading zeros, such as for a small decimal number, they are never significant and can be dropped and replaced with scientific notation. Captive zeros are always significant, and trailing zeros are significant if the number has a decimal point. So say 2400.0, that the zeros that lead the decimal point the zeros that lead the decimal point are significant, and the ones that come after the decimal point are not. And I mentioned that exact numbers have an unlimited number of significant figures. So, some examples. 65 million years. There are 2 significant figures because trailing zeros do not count because there's no decimal. 5,000.0 grams. There are 5 significant figures because the trailing zeros count if the decimal point is present. 0.005 meters. 0005 meters. This has also 1 significant figure because the leading zeros never count. However, 0.00050 meters has 2 significant figures because the leading zeros don't count, but the trailing zeros do. This leads us to rounding off. Once you've determined the appropriate number of significant figures, you should round off the number so that it contains that number of significant figures. If the digits being removed, if the last digit to be removed is less than 5, the preceding digit stays the same. And if the digit being removed is equal to or greater than 5, then the preceding digit is increased by 1. Important thing to remember about rounding is that if you're doing a series of calculations, you should carry the extra digits all the way through the calculation to the final result and then round. Otherwise, you may make an error. So here are some rounding examples. Number 8.4234. If you need 3 significant figures, you would drop the 3 and the 4, leaving 8.42. And if you only need 2 significant figures, then it's 8.4. You drop the 2, 3, and the 4. The number 14.780. For 3 significant figures, you write 14.8 because the 80 is dropped and the 8 rounds up. So it rounds 78 rounds up to 0.8. And if you have 2 significant figures, it rounds up to 15 because 0.780 rounds up to 1. And then finally, for 3,262, if you need 3 significant figures, you drop the 2 and add a 0, leaving 3.26 times 10 to the 3rd power. And if you only need 2 significant figures, it's 3,300 because you drop the 6-2, round up the 2 to a 3, and add 2 zeros, leaving 3.3 times 10 to the 3rd power. So, calculations can never improve the precision of an experimental measurement, and therefore there are rules for calculating for carrying significant figures through calculations. As a rule, a calculation is limited by the least precise measurement used in the calculation, and there are two different operational rules that govern this. So there is an addition and subtraction rule and a multiplication and division rule. The first one is the multiplication and division rule. So, a product or quotient has the same number of significant figures as the number with the smallest number of significant figures. So, you start by counting the number of significant figures in each number, and then you round the result of the calculation so that it has the same number of significant figures as the number with the smallest number of significant figures. So, for example, this calculation, 0.1021 times 0.082103 times 273 divided by 1.1. The result of this is 2.080438. So the first term has 4 significant figures, the second term has 5, and the third term has 3. The denominator has 2. Therefore, the result has to have 2 significant figures. Rounding this number to 2 significant figures involves dropping the last 5 digits, the 80438, and increasing the 0 to a 1. Meaning the result of this one is 2.1. Now, the addition and subtraction rule is that you keep the number of significant figures as the smallest number of decimal places. So you find the number with the fewest decimal places, and then you round the answer to the same decimal place. For example, this problem, 171.5 plus 72.915 minus 8.23 equals 236.185. The first term has 1 decimal place, the second term has 3 decimal places, and the third term has 2 decimal places. So the answer will have 1 decimal place. In this case, you would round 0.185 to 0.2, leaving behind the answer 236.2. Now, sometimes you'll have equalities in a calculation. Because they're exact, they don't have to have the same significant figure rules applied to them. Things like 1 minute equals 60 seconds. And I mentioned these before. These are also known as conversion factors. So conversion factors are a major part of chemical measurements and calculations because you are often given quantities in various different units because the way that you measure things is not always unified, and you have to convert and figure out how to add things and multiply them together. So a conversion factor is an equality expressed as a fraction, and it is used as a multiplier to convert a quantity in one unit to its equivalent in another unit. This conversion factor may be exact or measured, and both of the parts of the conversion factor should have the same number of significant figures. So, you can also use percent as a conversion factor. A percent factor uses a ratio of the parts to the whole in a fraction. So, we all know how to calculate a percent. It's the part divided by the whole times 100. Has the same units for the parts and the whole, and therefore is unitless itself, and can often be written as two factors. So for instance, if a food has 18% fat by mass, that means it has 18 grams of fat per 100 grams of food. And conversely, 100 grams of food has 18 grams of fat. Likewise, there are various parts per million and parts per billion, which measure their like percentages except for millions and billions instead of for 100. So a part per million is equal to 1 milligram per kilogram, and a part per billion is 1 microgram per kilogram of substance. For example, the maximum dose of lead in pottery glaze is 2 parts per million, meaning that for every kilogram of pottery glaze, there is 2 milligrams of lead in there. So, in the context of problem solving, say the average person in the United States consumes 1/2 pound of sugar each day. How many pounds of sugar would be consumed in 1 year? So this is a units problem. You start by finding the initial quantity given, which is 1 year. And then you want to know the number of pounds consumed in 1 year. So then you find the sequence of how you want to go about a pathway from the initial to the final unit. So the common factor in this case is the day. So you have a rate of 1/2 pound of sugar per day, and you know that a year contains a exact number of days. And so you can go from years to days and then from days to pounds. So for each unit change, you want to state the equalities. So in this case, every equality will have 2 conversion factors. In this case, 365 days is equal to 1 year, and 1 day is equal to 0.5 pounds of sugar. In this case, you go from years to days, and then from days to pounds. So this shows the location of those factors, and then you set up the problem. So 365 days per year and 0.5 pounds of sugar per day. So you have 1 year. There are 365 days in a year. The years cancel. You have 1/2 pound of sugar in a day. The days cancel because of the rules of division. So now you have 1 times 365 times 0.5, which equals 183 pounds of sugar. So the summary of this process is that you identify the known or given quantity and the units of the new quantity to be determined. You write out a sequence of units which starts with your initial units and ends with the desired units, or the unit pathway. Then you write out the necessary equalities and conversion factors, and then you cancel out the units in the denominators and numerators that match up, and do the mathematical operations such as multiplication and division, and then make sure that your units cancel properly and that the answer makes sense. So this brings us to the concept of density. Density is used often in science to represent many things. In this case, mass density describes how much mass is contained in 1 unit volume of a substance or in an object. It's a measurement of how tightly the matter is packed within that object. We generally use grams per centimeter cubed to represent the densities of solids and liquids. And for gases, we do grams per liter because gases are typically much less dense than liquids and solids. Density is equal to mass divided by volume. And this is shown in the units. So there's units of mass divided by volume. So to determine density, you weigh the object using a scale, and then you determine the volume of the object, calculating it if possible if you have something like a cube with measurable edges. You can also calculate the volume by determining its displacement in water, which is something that I will do in lab on Thursday. You immerse the object in water and then measure the new volume using something like a measuring cup or a graduated cylinder. And then that is the volume that you use in the denominator of the density calculation. And there's the equality. This is a picture of that same process. So you have a graduated cylinder. It contains 35.5 milliliters of liquid. You put a solid into the water. It increases to 45 milliliters, meaning that the volume of your object is 9.5 cubic centimeters. In this case, it is zinc. And then density can be used as a conversion factor in one of those unit conversion calculations. So if you have an object with a density of 3.8 grams per milliliter, then the equality is 3.8 grams is equal to 1 milliliter of that substance. And then you have two conversion factors. There is 3.8 grams over 1 milliliter and 1 milliliter over 3.8 grams, depending on the needs for that particular calculation. Here is an example of such a calculation. So iron has a density of 7.87 grams per cubic centimeter. If 52.4 grams of iron is added to 75 milliliters of water in a graduated cylinder, to what volume reading will the water level in the cylinder rise? So the number of things that you have here, you have 7.87 grams per centimeter cubed, which is the density, and you have a mass, and you want to find a volume. So to start, you have the things I just said, and you have a graduated cylinder with 75 milliliters of water, which we're going to call VI, or initial volume. To determine the final volume, you want to solve for the volume of iron. So density equals mass divided by volume, and volume equals mass divided by density, if you rearrange that quotient. So 1 centimeter cubed is equal to 1 milliliter. So you have 52.4 grams of iron. And we know, because we have been given the density of iron, that 1 milliliter of iron is equal to 7.87 grams of iron. So the grams of iron cancels in this case, leaving us with 52.4 divided by 7.87. And therefore, we have 6.658 milliliters of iron. Since we started with 75 milliliters of water, then adding 6.658 milliliters to that will result in 81.7 milliliters total, using the appropriate number of significant figures. So, the density of objects determines whether they will sink or float in water, for instance. So ice floats because the density of ice is less than the density of water. The same is true of cork. Water has a density of 1 gram per milliliter, and things like aluminum and lead sink in water because their densities are significantly higher. So this brings us to a learning check. Which diagram correctly represents the liquid layers in the cylinder? You have 3 liquids Caro syrup, which is 1.4 grams per milliliter in density, vegetable oil, which is 0.91 grams per milliliter in density, and water, which is 1 gram per milliliter in density. So the three options you have for option 1, you have Caro syrup on the bottom, water in the middle, and vegetable oil on top. For answer 2, you have vegetable oil on the bottom, Caro syrup in the middle, and water on top. And then for option 3, you have water on the bottom, vegetable oil in the middle, and Caro syrup on top. Now, for this question, they should be arranged with the highest density at the bottom and the lowest density on top, meaning that answer 1 with Caro syrup in the bottom and vegetable oil on top is the correct one. A related quantity to density is known as specific gravity. It's used oftentimes in the mixing of liquid solutions because it's more convenient of a representation than density, which can be difficult. The units can be difficult to manipulate in a clinical setting. So it just compares the density to the density of water, and it's calculated by dividing the density by the density of water at 4 degrees Celsius. It is unitless, and any substance with a specific gravity of 1 has the same density as water. So that's the end of chapter 1. Look for the quiz, which will be posted on, there will be a link posted on Blackboard. I will post another lecture describing how to complete it. And then on Thursday, I will be posting a video of the lab. And you will be expected to complete a report based on that video. Thank you for tuning in, and I hope everybody has a fruitful semester.